In the dataset used for our project, there are 3 labelled sets of sirens: fire truck, ambulance, and traffic or no siren present. Here is a display of 3 example waveforms for each of our labels to give an idea of the variation in our dataset. Once we have loaded the audio, we find the corresponding spectrogram. These spectrograms are what are used as input to the model, as CNNs are designed to extract features from images and struggle to extract features from raw audio data. Here we show an example audio waveform and the corresponding spectrogram. Here are 3 example spectrograms for each label, showing the range of variations in the frequency domain. This is a summary of our CNN model architecture, which we'll be using to classify our audio clips. This architecture resizes and normalizes the input spectrograms before passing through 2 convolutional layers with max pooling and dropout layers in between. The resulting feature maps are flattened and fed through 2 fully connected layers, with another dropout layer between them, before outputting probabilities for the 3 possible classes. These are the graphs of the training and validation loss and accuracy. Although the model was allowed to train for 50 epochs, the early stopping mechanism monitored the validation loss and stopped the training if it had not improved in 2 consecutive epochs, causing the model to stop training after 8. Finally, here is the full model confusion matrix attained during training and an example prediction bar chart. It is clear that the diagonal, representing where the model correctly predicts the true labels, has the highest number of values. Correctly identifying that a siren is present but getting the type of siren wrong is the most common error, suggesting that if we only cared about identifying whether or not a siren was present, the accuracy would be very high. TensorFlow models are not inherently compatible with microcontroller hardware architectures. Our model is significantly smaller compared to the TensorFlow applications found in Google's use case examples. However, there is no support on our selected platform, the Arduino Nano, for a full-sized model built with Python frameworks. Therefore, deployment required the use of pruning and refactoring to fit the model into a smaller one capable of running on ARM Cortex chipsets. We compiled a kit of 3 tools to achieve this over 3 steps. First, we converted the TensorFlow model to a TensorFlow Lite model, then to a TensorFlow Lite Micro model. Finally, we built a TensorFlow Lite Micro model object using the Arduino TensorFlow library. The majority of the refactoring occurs in the TensorFlow to TensorFlow Lite step, where, depending on the usage, the model can be converted into either a standard runtime for use with Android or Java SDKs, or to a customized runtime using any SDK. As there is no out-of-the-box support for the Arduino Nano, we had to produce the model as a C binary file containing a list of vectors. Although the system was able to differentiate between traffic noise and either of the siren sounds, the accuracy once deployed on the board was not satisfactory. Consequently, we turned to the Edge Impulse framework to develop a more precise model. This framework enabled us to fit and run a larger model on the BLE Sense board, resulting in improved accuracy on test data. To further enhance the model's performance, we trained it on audio samples captured directly from the Arduino microphone, rather than relying solely on the pre-existing dataset. This adaptation led to a more accurate and reliable sound classification system.
The demo system here is in 2 parts: the Arduino with the machine learning model and an interpreter that receives the classifications from this board and displays it in a human-friendly format as raw data and as a moving average that irons out any inconsistencies in the classification. When I run the interpreter, it can be seen that initial noise around the system, such as the PC fan or the street noise, is classified as traffic, and then when I play the samples, the classifications and the moving average become evident.